Module 1.3, Rational and Piecewise Functions. Objective 1, finding restrictions in the domain and determine if they are vertical asymptotes or holes in rational functions. Objective 2, finding horizontal asymptotes in rational functions. Objective 3, evaluate piecewise functions. And the last objective is to graph piecewise functions. Let's take the first objective. We need to find the restrictions in the domain to determine if they are vertical asymptotes or holes. So let's look at a couple of examples of this. The first one we're going to look at is a simple rational function. But we can tell by looking at this simple rational function that we know that x minus 3 cannot be equal to 0, or we'll have a 0 in the denominator. Okay, so I'm going to solve this, and we get that x cannot be equal to 3. So that is a restriction in the domain. And because it's not common in the numerator, in other words, we don't have an x minus 3 up here in the numerator, then it is a vertical asymptote. And that vertical asymptote is at x equal 3. And let me describe what a vertical asymptote is. A vertical asymptote is an imaginary line, kind of like a border or a state line, in which a function must stay away from or stray away from it. So if we look at our function is going to look like this. So notice it comes from negative infinity, and when it gets closer and closer to that line, it stays away from it and heads downward. And then it does the same thing except from the opposite direction, where it gets closer and closer to that red line but stays away from it. And so this is the first example of what a restriction can do. All right, let's look at our second example. Our second example is a function where we need to factor the denominator. So we're going to factor the denominator, and that should give us f of x is equal to x minus 3, and if I factor that denominator, that should give me x plus 3, x minus 3. So notice that this one is going to give us the restriction that x can't equal 3. And since x can't be equal to 3, and notice that it matches with the top one, so that means that this one is going to be a hole. And we'll illustrate that in just a second. The other one, this one right here, is giving us x can't equal to negative 3 if you solved it, and that would be a vertical asymptote. Now let's take a look and see how we can illustrate the hole and the vertical asymptote in the same graph. First of all, let's go ahead and get the asymptote drawn in there, or that imaginary line. Vertical asymptotes there, and let's go ahead and draw the graph. There's that line that does like that, and then this one does the same thing as the last one did, except right when it gets to 3, it's going to skip. There's going to be a little hole, and that hole is infinitely small. So that's the difference between an asymptote and a hole, is an numerator and the denominator. Then it is a hole. If it does not have a common factor in the numerator and the denominator, then it is a vertical asymptote. All right, now let's look at some examples that illustrate this. If you'll look at this first one, this one is fairly simple. Here we have that x plus 2 cannot be equal to 0. So we're going to subtract 2 from both sides, which will give me x that can't be equal to negative 2. This one does not have a common factor in the numerator, so we'll have a vertical asymptote at x equal -2. In our second example, we're dealing with the same thing. We've got to watch out for the restriction in our domain, so let's set 2x minus 3 can't be equal to 0. We're going to add 3 to both sides, so it gives us 2x is equal to 3, and then I'm going to divide by 2 on both sides. So x can equal 3/2. And in this case, it's not common factor in the numerator again, so this is going to be a vertical asymptote at x equal 3/2. Our next example, I see something in here that looks factorable, so let's go ahead and factor that. So we got x minus 3 on top. We got x. I got to factor out an x out of that. Okay, now here we're going to have two restrictions. One, we're going to have x can't be equal to 0, because if that one was 0, that would make the whole denominator 0. And the other one, x minus 3 can't be equal to 0, so if I add 3 to both sides, so x can't be equal to 3. Now notice that the x does not have a common factor in the numerator. You can't just take part of a subtraction of a difference like that. So the x minus 3 will have a common with the x minus 3, but the x will not. So this one is going to be a vertical asymptote at x equals 0, and this one is going to be a whole at x equals 3. Now let's look at our last example. Let's say we have, let's go ahead and factor that bottom. And here, again, kind of like example 3, we've got two restrictions. One, we've got x can't be equal to -7. And here, we've got x can't be equal to 3. This one, since it doesn't have a common factor, is going to be a vertical asymptote at x equals -7. And this one, since it does have a common factor in the numerator, is going to be a whole at x equal 3. Objective 2, finding horizontal asymptotes in rational functions. We got a rule. If a rational function is in this form, where just the subscripts for a's are just simply numbers, and we're dealing with, it's in descending order. Notice that you start off with n, and then it goes down 1, and then it goes down another one. And the same thing is true in the denominator. B is just simply different real numbers, and you have your x, and notice that D is also descending in this order. Then we have a couple of things that occur, so that just helps us kind of keep in notation what the numbers are. All right, rule 1. If the degree of the numerator, now that's the degree, that's the exponent on that x, if they're in descending order. If the degree of the numerator is smaller than the degree of the denominator, then there exists a horizontal asymptote at x equals 0. That's the first rule. Second rule, if the degree of the numerator, little n, is equal to the degree of the denominator, then we take the coefficients, which are a1 and b1. We take those coefficients and we put the numerator's coefficient over the denominator's coefficient, and that's where our vertical asymptote is. And the last rule is, if the degree of the numerator is greater than the degree of the denominator, then a horizontal asymptote does not exist. If you look in this example, the degree of the numerator is indeed smaller than the degree of the denominator. Therefore, we have a horizontal asymptote at y equals 0. Okay, with horizontal asymptote being the x-axis or y equals 0. If we looked at this function real quickly, just so that we have a general idea of what's going on here, we would see that as this function headed out toward infinity, it would get closer and closer to that x-axis. And the same thing runs true on this side. It would go out and would go closer and closer. Now, one thing we need to note about horizontal asymptotes is that in the middle it does cross, but there are periods where, and the period is pretty much from here on this direction, and the period is pretty much from here on this direction, where they continue to head closer and closer to that x-axis or y equals 0, but they never touch it. So you may have a little region in which it crosses, but then after it goes outside of that region, it's going to act like it's an asymptote. Okay. In our second example, we're given, notice that here we have the degree of the numerator is the same as the degree of the denominator. So what we're going to do is take the coefficients, which the top one is 2 and the bottom one is 1. So at y equal 2, we're having a horizontal asymptote. We have a horizontal asymptote at y equal 2. In our last example, here, if you'll look, our degree of our numerator is more than the degree of the denominator, and so we would have no horizontal asymptote. Objective 3, evaluating piecewise functions. If you'll look at our example here, we have a piecewise function that has 3 parts. We've got the top part, the middle part, and the bottom part. Okay? Our first thing that we're going to do is we're going to evaluate these functions. The first one we're going to evaluate if f of -4. Now, notice that this looks a lot like this, and the only thing that's been substituted is x and -4. So what I'm going to do is I'm going to look over here at my inequalities, and I'm going to figure out which one fits x equal -4. Well, this one says x is less than 0, this one says x is equal to 0, and this one is x is greater than. So isn't -4 less than 0? So it's going to fit the top one. So then all I have to do is, if I'm using the top one, I'm going to plug my -4 in where there was an x. So we're using that 2x. And 2 times -4 is going to give me -8. All right. Let's look at the second one. Again, I'm going to write in my little stencil here. We got f of x, and notice that x is equal to 4. We got that little substitution right there. So if we're looking, that's going to fit the bottom one, because that says these are for all x's that are greater than 0, and 4 is definitely greater than 0. And so we're going to use that x. We're going to use that x plus 2. So we're going to substitute 4 in, and that should give me 6. And so that will, f of 4 is equal to 6 then. And the last one, we're trying to find f of 0. Again, I'm going to write a little stencil in here. And we've got x is equal to 0. So that would fit that middle one, wouldn't it? Okay, and so all I'm going to do is plug in, since x is 0, I'm going to plug 0 in for that middle one. And that's going to give me a -2. And I've now evaluated one for each one of the 3 stipulations or lines that are in my piecewise function. Objective 4, graphing piecewise functions. Here we're given a piecewise function once again, and we're given the 3 stipulations. Now if you'll check notice that all the stipulations are dealing with 0. So a lot of things are going to be changing when we get to 0. Okay, so first of all, this thing is going to act like 2x, and as long as x is less than 0. So that's the left-hand side, or the numbers that are to the left of 0. All right. Normally, we would take and notice that the slope is 2 or 2 over 1, right? Okay, and that's going to be my slope. So usually that's the rise over the run. Okay, and so normally you go up 2 and over 1, but since I'm heading to the left, I'm going to go down 2 and left 1. Down 2 and left 1. And since this is just less than and not less than and equal to, there's going to be a hole here. So it's going to continue just like that, heading in that direction. Now, in the second stipulation, which starts at x equals 0, at the second stipulation, it starts off with slope. My slope for that second one is going to be 1 over 1 because there's not a number in front of x. So it'll be 1 over 1. So we rise 1, run 1, and that's my slope. And my y-intercept would be the number by itself. So this thing is going to, and notice that it's equal to. Okay? So at x equals 0, it's going to be equal to right here. And notice that's just a point because it only happens where x is equal to 0. So on that x-axis, only at 0 does it do anything. So it's going to be right there, which is where it crosses the axis. And then from there on out, it's going to do the last stipulation. So all the numbers that are greater than. So remember, that's going to be an open dot. Okay, and from there on out, it should be, my slope for that one is going to be 1 over 1 because there's not a number in front of x, and my b is going to be 2. So that's going to start right here. And notice that it's an open dot because it says that it's greater than. And then it's going to rise 1, run 1. Rise 1, run 1. And that's how that goes. So notice to the left, it's going to have slope 2 over 1, and it goes all the way to 0. It goes all the way to 0, not including 0. In the second line, it's going to act like x minus 2, but only at x equals 0. So that's where that dot came in right there. And then the last one, we have x plus 2 everywhere after 0, or once x is greater than 0. And so we've got slope 1 over 1 and the y-intercept of 2. And it goes off from there on up.